Okay, so welcome back again. Today we're going to start getting into the more interesting portion of this class. This is when we're moving beyond just going through and determining stuff statically. We're going to start going in and looking at the inverse kinematics of the system, namely how we can get the end effector to a particular destination. And that's what we're ultimately interested in when we're working with robotics, is getting that end effector where it's supposed to be. So we're going to do two things. We're going to look at the numerical methods that the book introduces, which are quite cumbersome. And then we're going to introduce cyclic coordinate descent, which the book does not introduce. And this is the method that we're going to be using in class to determine the inverse kinematics. This is going to get to the point where we're going to have many or much smaller assignments, but they're going to be much longer in length. I don't have this week's assignment written up yet, but as soon as I get it written up, I'll have it posted this afternoon. It will be two parts. One is to write the algorithm for the cyclic coordinate descent. The second part is then to use the DH parameters that you determine from that descent algorithm in order to plan motion from your initial configuration to your destination. Does that make sense? So essentially, once you figure out what the set of joint parameters are supposed to be, then the second part of the assignment will be to move from where you started to where you are wanting to go in the fewest number of steps possible. That makes sense? Alrighty, so let's, I'm trying something new. I have been noticing that my handwriting is quite poor, so I'm trying to clean it up a little bit by typing my notes up here instead of trying to handwrite them as I have been. So we've done this before, but let's go and do it again, just so that we can review what forward kinematics are and what the entire goal of looking at the forward kinematics is. So what is the purpose of the forward kinematics of a robot? What's the input or inputs?
Isn't it just going to be like a destination and rotation for our end effector and subsequent
Not for the forward kinematics. That's what we get out of it. So the output is the end effector. So what we end up getting out of the forward kinematics is the end effector location and orientation. And for that matter, we get the other joint locations and orientations as well. But the big one we're interested in is just the end effector. Okay. The inputs then are those DH parameters. So we put in the DH parameters. Those DH parameters include all of the information that we need to know in order to figure out where that end effector is located. Okay. How many possible solutions are there to this? Exactly one, right? So the forward kinematics, there is exactly one solution to any set of inputs. And therefore, we say that it's a linear system. Okay, we put in an input, we get an expected output out of that. And all this is just progressively applying trigonometry as we go down the chain. We express that trigonometry as a series of matrices and matrix operations, but really what we're doing is just going through and trig at these systems over and over again. So that we don't have to listen to people throwing stuff in the dumpster down there. What about the inverse kinematics then? What inputs do we have to start with when we are looking at the inverse kinematics? When we're dealing with the inverse kinematics, this is when we know the end effector location and orientation initially. So we start with the end effector, and the outputs then are the DH parameters. Now, not all of the DH parameters, specifically the joint angle and joint offset, depending on if it's a revolute or a prismatic joint. In our case, we know we're going to be working exclusively with revolute joints. Therefore, we only really need to consider the joint angle when considering the inverse kinematics as we're considering them. But in general, we should be able to use these inverse kinematics to determine the joint offsets as well. How many possible ways then can we achieve this? Well, I'm going to tell you that there are many ways. I should say many solutions to any set. Okay. Now, probably the least interesting is when we're sitting with a single link robot. Now, when we're dealing with a single link robot in a two-dimensional space, we can achieve a certain number of points within the workspace. But since the workspace itself is just the points along the circle where that end effector or where that robot rotates through, it's not particularly interesting. So let's consider a slightly more interesting question, and that is of a two-joint robot. Or I'll call this an actual example. And consider a two-joint planar robot with link lengths equal to 12. Okay. How many ways can we orientate the robot to position the end effector at the point 20, 0. How are you guys liking the typing thing? Is it better than the writing?
I prefer having a professor doing stuff on the board. It just keeps me more engaged,
Yeah, I've been watching the videos, and unfortunately the handwriting just does not come across real well. So in my actual classes and stuff, I will be doing board work and stuff, but I think in order to ensure that everyone on the other side of the camera can actually get something out of these lectures, I pretty much have to type the notes like this. Now, when we do the example like we have here, I can definitely, and I definitely will be doing the board work, but as far as the written material, I think typing it out in a word like this will work out pretty good. So, okay, so what's this going to look like? And let me run up the board real quick. And okay, I have one here. Okay, so what we have here is we had our robot sitting here at 0, 0. Now let me throw this red one away real quick so I don't reach for it again. So we have the base of the robot attached to the origin at 0, 0. And we want to reach or position the end effector over here at 20, 0. And we have two links. Each link is 20 units long, or I'm sorry, 12 units long. How the heck can we do this? Well, how many solutions are there for one? There's two, right? We can have the solution for, and I am attempting rather poorly to indicate that these two links are the same length. So I'll do that just to let everyone know that they are in fact the same length. So we have two possible solutions in this case. The one solution, we can have a positive base angle and then turn south to reach that destination. The other possibility is we can have a negative base angle and turn north to reach that destination. That makes sense? So how the heck can we go through and figure out what the joint angles have to be? Pythagorean theorem. We can go through and make a bunch of right triangles out of this. Keep in mind that this should be coincidental since we're forming a quadrilateral here. But anyhow, in this case we can apply the Pythagorean theorem over and over again. We can apply our trig properties over and over again. Since we know that this is a 12 and this is a 12, this is a 12, this is a 12, well, we're going to reach, we have an isosceles triangle there, therefore the vertex is going to be halfway across the base, meaning that this is going to have a length of 10 and 10 respectively. Okay. With that being said then, we can go through and find either of these base angles by applying one of the trig relationships. In this case we have the adjacent side and the hypotenuse. Therefore we can find the angle alpha by taking the arc cosine of the base to the hypotenuse. So what do you guys get when you take that angle? I was in my office wondering if anyone was going to have their calculator with them.
33.5.
33.5 degrees, okay. Okay, and down here in the lower portion, what's this angle going to be? Just so that we can say we did it. Negative 33.5 degrees, because it's just pointing down south. Okay, how is this second angle going to be oriented? Well, we know that the frame is going to be affixed like that. Therefore, this is going to be a negative angle. Okay, what's that negative angle going to be? It's going to correct for the 33.5 degrees we adjusted, and then turn it a subsequent 33.5 degrees to get it pointed back at the destination. So our theta 2 then, I should probably call this theta 1 and theta 2. That'll correspond much better with what's in the notes. This will then be a negative, what is that, 67 degrees. And down here, we see that this second solution will be a positive 67 degrees, as long as I get the math right. Yes, that's correct. Okay, so even in this simple case, we have two solutions. How often do we deal with robots with two links? Not very often, okay? How many links do you need in 2 dimensions to position a robot or position an effector? 2. Okay, so in 2 space you need 2 degrees of freedom to position it anywhere in this robot or in this frame. But we know that we're generally interested in both position and orientation. Therefore, in the plane we need to have 2 joints to position it in X and Y, and then 1 to orientate it to get it pointing in the correct direction. Okay? So that means almost always the very minimum number of joints that you'll run into is 3. Now, that third joint can not only provide you that additional degree of freedom to provide the orientation, but it can also introduce a degree of redundancy in the robot. And that's what we're going to be seeing in our assignment this week, is that we're going to have a high number or a high amount of redundancy in our chain. What is redundancy used for? So if we have, in our example, we'll have 5 degrees of freedom in a planar robot, what would those additional degrees of freedom be used for? Let's say that we need to reach around an object. We're still in the plane, but we've got an obstruction right here. But with additional degrees of freedom, we can reach around that obstacle in order to avoid it altogether. So when we're dealing with a robot with redundancy built in, that redundancy can be used to navigate around obstructions within the workspace, okay? And so when we go through and begin this week's assignment, keep in mind that even though we typically only need 3 degrees of freedom to position in the plane, to position and orientate in the plane, we oftentimes have a certain amount of redundancy built in just to avoid obstacles, okay? Okay, so let's step this up a bit then and consider the same problem, but consider a 3-link robot. Okay. Same question. How can we go through? Let me scroll up there. How can we repeat this problem, but now with 3 robots? And how many solutions are there going to be? So we have the same setup to the problem. We still have our base attached at 0, 0. We still have our destination sitting over here at 20, 0, but now we have 3 links and 3 degrees of freedom in order to get there. So first off, the easy question, how many solutions are there?
It seems like they're gonna be a lot more, but
There's an infinite number of solutions. Okay. Now, in our robot, we have to keep in mind that our joints are usually driven by stepper motors, and the stepper motors have a resolution of typically 1.8 degrees per step. So that limits the number of possible solutions that we need to concern ourselves with. But the thing is that if we just consider the general case, we can have truly an infinite number of solutions in this particular problem. Okay, we could have the solution where we have something looks like that, where we have a trapezoidal path set up here. We could have something where we have 2 arm segments that are in line with each other. Those 2 arm segments could actually be aligned up front here. We could come up with something where maybe we're back this way a little bit and on over there. So there's going to be many, many solutions to this problem. Okay? Give me one solution that, or one easy solution that we could take a look at. If we had to go through and solve this, what would be the easiest way to do so? Try to come up with some joint angles to reach that destination. Well, the easiest thing to do is make one of them 0, or predefine one of them to be something, right? Okay? Doesn't really matter what we predefine that first angle to be, but we have to say that it's something. Does it have to be the base angle? No, we just need to eliminate some of the information in the problem. We're reducing the number of unknowns by assuming something. So let's say that we do decide to set the base angle equal to 0. That means that this first segment, which is 12 units long, is going to be positioning the rest of the robot with reference to the position 12, 0. That makes sense. And now how are we going to go through and determine the remaining 2 joint angles?
same way we did the first
The
example.
exact same way we did on the first one. The only difference is now we're only going to have 8 units for our base width, and therefore our triangle is going to look something like this. So we're going to have 4 units here, 4 units here, and we can go through and do the exact same thing. We can say that this angle will be equal to theta 2, which is going to be the arc cosine of the base to the hypotenuse of 4/12. What's that give us?
70.5 degrees.
70.5 degrees. So we could say plus or minus 70.5 degrees. And then what would our theta 3 end up being? Again, it would be twice that, pointed in the other direction. So our theta 3 then would be 141 degrees, so minus or plus 141 degrees. Because we know that, just like before, we have a second possible solution given this initial base angle of 0. Okay. Now what happens if we decide to pick something other than 0 for our initial angle? If we pick 1 degrees, then we have 2 possible solutions. If we put 2 degrees, then we have 2 possible solutions. There's only one instance in which we'll have a unique solution. And again, that's when we shoot up here and have those 2 subsequent lengths aligned. Okay? But with this being said then, if we just go through here and take a look at the different ways that this can be arranged in order to give us a solution, there are in fact an infinite number of ways that that can be achieved. What I have done is I've written a short little script here to demonstrate this. And so I need to this isn't necessarily part of your assignment this week, but it does really help to illustrate. Okay, so what I have done here is essentially set up 2 loops. The first loop is moving joint 1 between 0 and 360 degrees in increments of 0.2 degrees. Okay. I could go through and increment this in 1.8 degrees as I had previously advertised, and that would be more appropriate for a lot of the stuff that we do, just because of the characteristics of the stepper. Now, one thing to note on stepper motors is even though they're typically set up with a resolution of 1.8 degrees per step, you can have a reducing gear on them or belt to change that resolution. If you have a the shafts coupled to a larger diameter pulley, then you're going to be, let's see, what would that be doing? It would be increasing the resolution by decreasing the step angle. If you go from a larger diameter to a smaller diameter, so if you have a larger pulley on the stepper itself, coupled to a smaller pulley, then you're going to be decreasing the resolution by increasing the angle that you're stepping through. Okay, so with this then, I'm going through and adjusting theta 1 between 0 and 360. I'm checking the distance to theta 1. In this case, what I'm doing is I'm going through and saying, okay, well, how far is it to the subsequent join, to the end effector? If it's less than or equal to 24, then I know that I can reach it. Why 24? Well, that's the sum of the next 2 lengths, right? If the if it's within the maximum reach of the next 2 lengths, then I know that I can possibly get there. So once I do that, then I'm going to go through and increment theta 2 from 0 to 360 degrees. Perform the same type of thing here, except for in this case I'm using a tolerance value. So I'm looking at the absolute value of the square root of the distance, absolute value of the distance minus 12, and checking to see if that's less than our tolerance value. Now, why am I doing that?
See what's the closest value. Getting the joint to the position that's the closest to the end the end effector can reach it.
Exactly. So what we're doing here is we're saying that this is the maximum deviation away from our deviation, away from our destination that we can allow. So in this case, this could be 0.01 inches or 0.01 millimeters or whatever the case is. This is just the maximum allowable deviation that we're allowing our robot to have, okay? So if it was millimeters, that would mean that we were allowing 10 microns of variation between the desired destination and the actual destination. That makes sense? And for this reason, we can position these very accurately. I mean, if we have any tolerances built into the robot, we have to take those into account as we go through the chain. But the thing is from the positioning algorithms, we can create these to be very, very accurate. Okay, after we do that, then we're going to go through and plot the destinations and then draw. This n variable is just counting the number of solutions that we find, okay? And keep in mind, this is with a 0.2 degree step resolution on theta 1 and theta 2. So when I run this, we have a ton of solutions. This, even though it's kind of cool and reminds you of screensavers from the 90s, it's not intending to be that. This is going through and actually drawing each of the subsequent solutions to this problem. If we were to go through and redraw this with, say, a 0.1 or a 0.05 degree step, it would take significantly longer. One thing that I'll ask now is it necessary to know all of these solutions? Not at all. All we need is one, right? Well, I should say we need to know one good solution, okay? And in order to achieve that one good solution, it kind of looks like, is it MasterCard or Visa? MasterCard symbol? Almost. So if we know one good solution, that will get the job done for us, right? So it's really not necessary to go through and calculate all the possible solutions. In fact, it's an impossible job to do because regardless how far you go, you know that there's always another solution sitting there halfway between one of the solutions that you calculate, okay? This is kind of cool though, and I'll speed it up quite a bit here when it's done. By the way, how many of you did something like this and got it to go through and start plotting stuff for you? So if you happen to close the graph before it completes and it's in the middle of the loop, the only thing that'll do, it won't stop the function. What it'll do is it'll go through and start running you through the plots without holding the pre-existing information, okay? So if you do want to break out of a drawing routine, you have to do the Control-C in your command window in order to get the job done, okay? So I will go through and change this to, let's just go ahead and do the 1.8 degree step resolutions just for the heck of it. Now, what's the nice thing about 1.8 degrees in relation to a full rotation?
It'll be an even,
Yeah, it'll give you an even number of steps to complete one full revolution. In fact, with a step resolution of 1.8 degrees, that means that you need 200 steps to complete a full revolution. And that's part of the reason why the engineers back in the day developed stepper motors with a 1.8 degree step resolution, because it was an integral or integer multiplier of the 360 degrees for the rotation. So in this case, I'm changing it to 1.8 degrees, and we can see that we have many fewer solutions, in this case only 16, okay? So that does speed up our calculation a lot, okay? Then, let me move it down a bit, that's better. If we go with the characteristics of the motors and of the robot that we're dealing with, it definitely does speed our calculations up significantly, but even then we don't need this much information, okay? We only need the one particular solution. One other thing that I did in my office this morning that was kind of cool, this related, is I started moving that destination around. The way I wrote the script, and you guys can play around with it, I have the destination specified here. Oh, and that's incorrect, that was with the destination. So, let me change it back down to the, I'll just do 0.5, that way it fills in a bit more detail. Okay, so there's our solution for our destination of 20, 0. And if we go through and start moving this around, say we want to put it at 10, 15, we can see all the possible solutions associated with that destination. That makes sense? So pretty cool. I mean, it gives us a real kind of cool way to look at these possible configurations, but it's just not particularly useful to us, okay? It definitely does go through and illustrate all of the solutions, just not, we have to recognize the fact that we don't need to know all the solutions. Good? Okay, so what do we really need then? I suppose I've said this too many times already. We only need one good solution. And there's a couple things that I need to point out here. And I've already made these, points. Actually, no, I haven't. So two things we're going to do in order to simplify our algorithm development is we're going to, number one, we're going to determine position of the end effector only. That means that we're not going to factor in the algorithm that we're going to develop could be used to factor in the orientation of the end effector as well as its position, but it's just not something that we're going to try to implement. We've only have a week to do this assignment, and by factoring in orientation too, it would really make it quite difficult to factor in both elements. Second thing that we're going to do is we're going to consider only planar robots. Algorithm. Only to planar robots. Okay. As is the case as before, we could very easily implement this in 3 dimensions, but we don't need to. We can get the point across, we can learn how this algorithm works by applying it only to 2 dimensions. Okay, 3 dimensions is great, and ideally that's what we would do. But the issue with applying this to 3 dimensions is that when we do a mouse click, we can only generate a X and Y coordinate. We can't develop a Z coordinate with that as well. So for that reason, we're only going to concern ourselves with planar robots, therefore on the XY plane. Good? Okay, so if we want to develop an algorithm, and let's see, if we want to go through and develop an algorithm, what can we do? Did you notice on that script that I just got done illustrating that I didn't necessarily go in and calculate? I didn't have a arc cosine anywhere in that process. What did I do? Let me pull it back up here. Did I actually go in and say, okay, set this to 0 and calculate, set it to 1 and calculate, and go on so forth, so on and so forth? No, what I did was I set this up as a search algorithm. I incremented through the angles and then found the angles that suited the job. Okay. So what I ultimately did here was I just went through, chose a theta 1, chose a theta 2, checked to see if it would get us to the destination, and then moved on to my next theta 1 and theta 2 to see if it would get us to where we were trying to go to. Okay. So when we go through and develop the algorithm will search for the joint angles. And again, since we're only considering revolute joints, it's only the joint angles we need to find. That will achieve the destination. And I should say that will position the end effector at the destination. Okay. What process are we going to do? We're going to adjust an angle to do what? What was the point here? We're trying to minimize the error, aren't we? We could go through here and throw some calculus at this and say that, okay, well, we have an arc, we're trying to minimize the distance on the point tangent to that arc and the destination if we wanted to, but we're not going to worry about that. All we're going to do is go in and try to we're just going to go through and perform a distance measurement from the end effector to the destination and keep on adjusting a joint until that distance is at its very minimum. Okay? So we're going to adjust the joint until the distance from end effector to destination is minimum. Okay, then what are we going to do? Then we're going to move to a different joint and do the same thing, right? So to different joint and adjust for same effect. And we're going to keep on doing this until we actually get that end effector sitting right on top of the destination. Now, there's a little bit of information that's lacking here. What is it? This is the general algorithm to get the job done. But what it's missing is a particular order to implement it. Where should we start adjusting? We need to have a procedural approach in order to set this up so that we can write a computer program out of it. If we can set it up so that there's a flowchart that goes along with it, or so that there's a very systematic approach, then we can implement it in our code. Okay. So that's where the cyclic coordinate descent algorithm comes into play. Okay, this is nothing more than the preceding algorithm, except for it establishes the process that we go through in order to arrive at the destination. So what it says is it adjusts the joint angle of the last joint until the distance from the end effector to destination is minimum. Okay. Then what? Move to previous, well, I'll say the I-1 link. Oh, I know, how about preceding link and perform same. Okay, so we're just going to move back to the preceding link, do the same thing, adjust that joint so that we minimize the distance to the end effector, and continue working backwards through that link to get the job done. Okay.
Why don't we start at the first joint? Wouldn't that make the most difference?
You know what, that's exactly what, that was the exact same conclusion that I came up with as well. If you adjust the first joint, that's where the largest portion of your motion is going to occur on. Okay. However, what I have noticed is that when you do adjust the first joint, ultimately, so let me run up the screen here real quick. Okay, so let's say we have a three-link robot that starts off in this initial configuration, and we're trying to reach this point here. So the two options are to start at the last link and move back to the first link, or start at the first link and move out to the last link. So if we adjust the first link, we might end up with something like this. And then subsequently from there, we might end up with something like that, and then subsequently something like this, and then we're going to have to go back and adjust that base link again in order to refine each of the joints.
I guess that makes sense. You'd want to position that end effector first.
Right. So ultimately, this makes sense. This process does tend to require more iterations in order to arrive at that destination location. Okay. And it's because you're pretty much guaranteed to have to adjust that base angle multiple times. Whereas when you start at the final link, you may not even have to touch your base joint in order to reach that destination. Okay? Just by going through and adjusting this guy, coming back, adjusting here, moving through, and so on and so forth. Okay? So, what was that? No, dang it, I thought I had like class involvement for a second. Okay, so ultimately, when the researchers developed the CCD algorithm, I imagine they probably considered the exact same thing. Why not just start here? And more than likely, they reached the exact same conclusion. If we adjust our final joint first, point it in the direction of the destination, then subsequently move backwards through the chain, we actually end up with fewer total calculations in order to arrive at that destination. Good? So, with that in mind, I'll put the only other part to this algorithm, and that is to continue through base joint and repeat if needed. So just because we're hoping that this is more efficient doesn't mean that we're going to get all the way down to the base joint and have arrived at our destination. We may have to go through this process twice or 3 times even in order to get there. But generally, after you've gone through the first time, you're essentially at that destination. Okay. The second and third time through, then you're just refining or minimizing the error, which very seldom requires a subsequent adjustment of every joint. That makes sense? So, before we actually get to the development of the algorithm itself, there's a couple things we need to be able to do. The homework assignment is going to require us to first use a set of DH parameters in a random initial configuration. Actually, let me pull up the assignment as I have it setting right now, assuming that I saved it before I left my office. So there we go. So I went and replaced my desktop, and in doing so, they upgraded me to the next newest version of Office. So now I have to, as if it wasn't irritating enough learning the last new version of Office, now I have to learn the next new version of Office. So.
Is on campus?
Yeah.
I thought IS didn't want Windows 8 on any computers yet.
Not Windows 8, but they're putting the Office 360 or I don't even know what it's called, but they're updating to the new version of Windows, or to the new version of Office. Okay, so what you're going to do then is you're going to go through and use this particular set of DH parameters to represent your robot. Now what you're going to do is you're going to assign a random set of joint angles within this range in order to have an initial configuration. That way you're not starting in the same location or in the same orientation each and every time. So in order to do this, there's a very useful command. It is just the rand I. Okay? My uncle's name is Randy, so I find it kind of humorous here. So probably not spelled with an I at the end though. That seems rather female-like for some reason. So what we can do here for theta 1 for our initial calculation is we can say that theta 1 is equal to, let's see, it's got a total range of 360 degrees, but if we want it to go from negative 180 to positive 180, so we can say that theta I, or theta 1 is equal to rand I. We want to pick a value between 0 and 360, and then we want to move it backwards by 180 degrees. And so what this will do is if we have, if this random number generator chooses 360, it'll take 180 off of it, giving us our upper boundary. If it chooses 0, we'll be at our lower boundary, putting us in our relative locations. Okay. Now, when I set this up on the homework assignment, what I did was I said that theta, as expressed as a vector, was equal to rand I 360 minus 180, and then rand I, that's a 270 degree interval, minus 135, and then 0, because our last theta angle is 0. We're not reorientating that final frame of our robot. That makes sense? And then with this theta vector included in our robot, then I can just say that our VH parameters is equal to, let's see, 0, 0, 0, 0, 0, 0, 0, 40, 30, 20, 10, 5, and then theta. And once we have our initial VH parameters set up, we can just go through and plot our setup exactly as we did before. That makes sense? You could also save yourself a step here and just say that you have Randy 360 minus 80, 180, and so on and so forth across the row. In which case you'd be referring to the particular elements within your VH parameters matrix. The reason I set it up like this is so that I could say theta sub 1 corresponds with theta sub 1, theta sub 2 corresponds with theta sub 2. It was easier for me to keep track of. That makes sense? Next thing we're going to do is enter a destination by clicking on the plot area. So after you have graphed your initial robot configuration, you're going to click on the plot area to provide it a destination. And with this destination then, what you're going to do